All right, guys, we're gonna get started. Okay, so this is the second week. We are currently recording, so you can see that. I will be posting these videos today or tomorrow. All right, so this is the second week. I believe next week, Monday, is Labor Day weekend, right? So Labor Day break. So we have no class on that Monday, all right? So just be aware of that. What I'm going to do today is I'm going to assign two homework assignments. So the first half will be a set of word problems, and then the second half, we're going to start getting into tensor operations with Anaconda. So I'll go over that. And basically, you're going to have the two homework assignments. One is going to be due a week from today, and one will be due 2 weeks from today. Does that make sense? So even though you're on Labor Day weekend, you can work on that assignment. All right. So let me go over this on Brightspace first, just to indicate. And then, of course, today I'll do examples of what I have in mind for these two homework assignments. I haven't created the problems yet, but look for them by Wednesday or so. All right, so let's start with Brightspace here. So as you know, there's two sections in here. I'm just gonna look at section 1, but section 2 should be a copy, an exact copy. So I'm gonna go to content here. All right, so these are the two modules in question that we're gonna do today. So the first half of class today, I will do ML word problems. Okay, so you can see here I haven't created the assignment link yet, but I'll do that. This is the assignment that will be due a week from today. Got it? Makes sense? All right, so I'll go over this, the ML pipeline. That's kind of a little bit of the theory that we're going to look at today. And then we're going to spend the first hour and 20 minutes just going over these in-class problems, where you guys can ask me, another problem. And basically, we're going to do the same thing we were doing last week. What is X? What is Y? Right? So this is something that I think is really important. You may know how to do CNNs, right? Or you may don't know everything about linear regression or transformers, but if you don't really know how to take a problem and start to simplify it to convert it into a machine learning problem, you're going to be in trouble, right? So I don't do this for the whole semester, but I do this at the beginning. So this will be these are the examples that we're going to look at today. I think we've done one already, and so we'll pick another one and start thinking about it. And that will be the first hour and 20 minutes. I'll just show you, again, what I expect for that homework assignment. There is no right or wrong answer as long as you state your assumptions. And really, it's really important that you state the dimensions of the matrices, right? Everything in deep learning, in machine learning nowadays in neural networks is about the dimensions. That's really critical. And it's the one thing that people, if you know how to do that really well, you're going to do well. And if you don't understand how to do that, then you're going to be in trouble, right? That's actually the hard part. Okay, understanding those dimensions, because the problem is you may know how a CNN works, but your data, your problem is going to be very different, right? So, you never know what kind of problem you're going to have to work with. And so converting that into that X and Y is critical, all right? And then getting all those dimensions from there. All right, so anyway, so we'll do word problems for the first hour and 20 minutes. And as I said, I haven't really created these, but this document that says HW here, homework, this will be I'll create from 3 to 5 problems, and I'll just have to think about what I'll do, okay? All right, so any questions about that? You'll create, for this assignment, you don't have to do any coding. You can even just take a sheet of paper with a pen, pencil, write it out, and then take a picture of it, load it. It doesn't matter to me as long as the answer is correct, okay? And just make it clear so I can read it and all of that. You'll submit a report, either a PDF or a Word document. And this will be due, as I said, 1 week from today. Is that clear? Any questions on this assignment? All right, great. The next, so the next modules during the second half of today, we'll start coding. and we will start. I call this tensor operations, basically. Okay, so machine learning. If you've ever maybe thought about it or taken a class, you've probably seen that it involves a lot of matrix multiplications, right? Now, some people will take linear algebra, and that's great, if you've had that, but you don't really need to know all the concepts of linear algebra to do deep learning. In fact, you only need to know a few operations, okay? I feel strongly that that's really important, okay? If you master that, that's the difference between you solving a problem efficiently and not, okay? So I will go over today tensor operations. As I said, this is basically in NumPy or PyTorch. Those are the two languages that I'll be using this semester. And so I'll start to introduce today some problems, okay? So I'll do some examples. I'll show you how to, some of them will be super easy, okay? So we'll start with Anaconda. We'll do some NumPy problems, just build up some skill. And then if time permits, we'll also do some PyTorch tensor operations, basically. At the end of the day, what I would say with machine learning is you don't have to know the whole of linear algebra, but you should know these operations well. And sometimes you should just develop some muscle memory, right? And to develop muscle memory, you have to do a lot of problems. You see what I'm saying? So I have a link here, and I've created this GitHub. It has about 109 tensor operation problems, right, that I've been working on. And so you can just go through them and just kind of do them, as an exercise. I will I'll start with 1 to 15. So you can see 1 to 15. And I have all these, some are very simple, but they're just building up on NumPy or PyTorch. So I strongly, although this is not the homework, I strongly recommend that you go through as many of these 109 problems, okay? Got it? And then I will, of course, create some problems out of these, 3 to 5 problems that I will give you some, word discussion there, and you will have to solve it with either NumPy or PyTorch. Does that make sense? Any questions about that, guys? All right, great. So yeah, so you'll see me, I'll start with, 1 through 15 or so, and I'll just show you all the mechanics of how to get started with Jupyter Notebooks, Anaconda. Hopefully you've all, if you have your laptop, you can follow along, or you can do this at home, etc. And then at the end of class, I will create an assignment link here. I'll call it Tensor Operations Homework. And then you can expect to see a Word document here at some point in the next 2 days with 3 to 5 problems that you'll have to solve. And it'll be due 2 weeks from today. Okay. And then, definitely use that Labor Day break, those 3 hours of class or whatever, and try to go through all these problems as many times as you can. Don't even just do them once, but do them as many times as you can. Develop a feel for these operations, okay? And then because, when we come back, we'll start getting into PyTorch and then building up ever more complicated neural networks. Remember that our goal in the class is to build a transformer, the GPT part of a transformer from scratch, right? So that's it. So, one goal, but that requires a lot of little pieces that we need to understand. Make sense? All right, great. So we'll start, as I said, with the first half. So I'm going to go over here, table of contents. And I'm going to take a look at this. ML word problems. So I'll be using the electronic whiteboard here and kind of just try to solve the problems just like we did before. So I'm going to click on in-class problems. And once again, oh yeah, actually, before I start with this, I have this, the ML pipeline. So this PDF actually summarized, how you can look at machine learning. So we'll start here, right? So you may have seen this before. I like to use this a lot. This is kind of a screenshot of what I think of machine learning. And as you can see, I've highlighted in yellow an arrow here, X and Y, right? So, what I'm trying to do is, create like a template, right? So that you always know how to approach deep learning in particular for this course. Find that X and that Y, find those dimensions, and that will help you along the way to develop your algorithm, okay? All right, so basically the machine learning pipeline, so it means it goes from here all the way to the end, right? So first of all, you'll identify the problem, usually, right? So that's what we're doing with the word problems, right? And as you can see from identifying the problem, you go to X and Y, which is, the way that you're representing your data. Usually machine learning involves some kind of a training, et cetera, and a correlation between inputs and outputs, right? So that's the goal. During that process, between identifying the problem and getting the data set ready for machine learning, you'll usually have a lot of steps. You'll have collected data, feature engineering, data processing, scaling, feature ranking, dimensionality reduction, and so on. And you don't always have to do all these steps, but in general, these are some of the steps that you can do, okay? So, so we're doing the word problems, and I'll just take as an example here images, because it's like the traditional thing to look at. So we want to solve a problem related to images, so we want to collect some data, so that probably means having some images, right? So we're going to have images that need to be labeled. So where do we collect this data from? We have social media, web crawlers, scraping, images that you just took with your own camera for your own problem, etc. Right? So that's what that means. So for the most part in this course, I will provide you with data sets, although, we may do one example where you have to collect your data. And the point of that is really just to show you how difficult that is. Okay, data science, the hard part is in the data. Like, you can always just take a CNN or, something like that that's already there and just adjust some of the dimensions, but the data, getting it ready can be challenging sometimes. All right, then we have something called feature engineering, and that basically just means representing your data as something called the vector space model. It's like a format that you can think of for representing your data, okay? Now, when we're doing this X and Y, as I'm showing you, you're already automatically creating this vector space model, okay? You'll see me talk about this throughout the semester, but just know that when we do this and arrive at X and Y, we are creating a vector space already, okay? And so that's really nice because the vector space model is like a geometric way of thinking of your data. And so then a lot of geometric things apply in that vector space, such as the distance, like the distance between you and you, right? Provides you some information. So that's used, when you can use the vector space model for specific algorithms like KNN, et cetera, the K nearest neighbor. Although we're not going to cover that topic in this course, since our focus will be mainly on neural networks, okay? But within the context of neural networks, you can use vector spaces too, all right? So I'll mention that at some point later, okay? So it's a very handy tool. And as I said, by creating X and Y, you already have a vector space. All right, then we have something like pre-processing, and pre-processing just means doing something called one-hot encoding, for instance. So that's a technique that, again, we will see throughout the semester. There's a lot of pieces, right? But, I'll get to it, and because we will have to represent our data like that. Neural networks will need to have that. So we'll talk about whether we have labels or we have some kind of regression data or something that we're correlating. Sometimes you correlate an input to an output, and that may just be like words, for instance, right? So we might do that, or images, right? Then you clean the data. Cleaning the data as well. At the end of the day, as you know, with signals, you have the noise and you have the information, right? So we want to remove as much noise as possible, simplify the problem. Transformations, that's what I would say a lot of the time neural networks are doing, right? So that's why transformers are called transformers, right? That you're from one layer to the other, you're just transforming. So transformations are pretty important, okay? Scaling, I always like to put this box here, and you can see I wrote important over here. Scaling is usually really important for neural networks. A lot of the incremental advantages in deep learning happen because of scaling. And what that means is when you have values from 0 to 5,000 or 0 to 100 or 0 to 1, you scale them all to be like within a range of 0 to 1 or -1 to 1. Neural networks really like that. And not just in the inputs and the outputs, let's say, but also within the layers, right? So that's why you have steps like batch normalization right after layers. That helps out neural nets, all right? So you'll see me later on, talk about standardization, normalization. We'll do this in the code, and we will also look at some point at batch normalization, which is normalizations within layers and so on, right? So scaling, really important, okay? When you do your project, you always really scale your data. All right, then other steps that you can do or sometimes you don't have to do are feature ranking, dimensionality reduction. So these were very popular techniques in the past. Nowadays, it used to be that because we had limited computing power, right, we really wanted to compress our data. That was used to be the standard practice. But nowadays, computers are so powerful, right, that it's better just to give it everything. So it's kind of the intuition. Let's just give it everything, and let's squeeze every single piece of information out of our data. Because sometimes with these techniques, singular value decomposition, feature ranking, PCA, you do lose some information, all right? So they're still there, and you can use them, right? But and that's fine. But I generally the approach is throw all the computing power at it and let's see how much we can get out of it. All right, so these are in general the machine learning pipeline that you can use just to get to the point where the data set is ready for ML. All right, and that's your X and Y. So that's the thing that we will be doing today with the word problems. All right, I'll grab one, another problem. Maybe we'll have time to do 2 or 3. And that will be it as far as those word problems for the semester, but hopefully that'll be clear enough for you to understand them. Then once you have your X and Y, the beauty of it is that you can actually take that data as a text file, as a CSV or something like that, and you can feed that into many machine learning algorithms. There's a tool called Weka that actually you don't have to code anything with it, and it'll take X and Y, right? You maybe have to tweak it a little bit. So, and also neural networks will take the information, okay? So I'll, like I said, most of our focus will be on neural networks. So I'll skip the perceptron, but we'll start with linear regression all the way up to transformers this semester. There are other machine learning algorithms that you may have heard, such as naive Bayes, KNN, and such algorithms. So those are covered in our undergrad class 365, but I won't be covering them in 520. All right, so and then the types of problems, once you have all these algorithms, you'll feed your X and Y, and then really the question you have to answer is what kind of a model are you trying to build, right? Are you trying to build a model that predicts classes, a model that predicts regression values, or a model that predicts words, right? And how does that work, right? So or it generates images also, right? So these are the things that, we'll start obviously with regression values, then we'll build up to some classification values. And then as you probably, know with transformers, they generate text, right? So we'll take a look at how that works, for the semester. And that's kind of the goal. So this part can be tricky, all right? Especially as we get into the more advanced algorithms, it's not just like classification. We'll have to think a little bit more of how that works, right? And it's complex, but hopefully we'll start to understand a lot of parts of the algorithm. All right, and then finally, and very important, you always evaluate performance, okay? And so we're going to have performance evaluation of your models, and then you have a lot of metrics depending on whether you're doing like a regression, which might use something like the R-square or root mean squared error, or we have classification where we have precision, recall, F-measure, the confusion matrix, or if we're doing much more complex tasks like language translation, then we have a set of metrics for that, like the blue score, and just more advanced metrics. All right, so there's a lot of metrics for every problem. in machine learning, whether it's normal machine learning, generative AI, or whatever it is, you better believe there's a nice set of metrics that people use, because there's a lot of competitions, companies that, propose these products. They need to go to like a venture capitalist, right, and show them some metric that says, yeah, our model is really good, right? So if you're building a math GPT, okay, you can't just say this is awesome, right? You have to go in and show them, here's my metric, and you can see that it does well within this. Okay, so we'll talk about that as we start to build up on the neural nets and so on. Any questions? So this is the general machine learning pipeline. Okay, so always try to frame your thoughts within this idea. Right now, today, and until the end of the first half of today, we'll read some problems and just arrive at the X and the Y. Okay, and do this exercise and then move on. So I'm going to go back to Brightspace here. All right, so I have my in-class problems. So these are just problems I've done in the past. I'll create a new set of problems for the homework, but I'll repeat these for the previous lectures. And you guys can tell me one. I think the last one we did was breed of pets. What was the data that we used for that? Do you guys remember? Did we use like measurements, right? Measurement. Yeah, the length and so on. Okay, great. So I want to do today a image one, just because that's very classical. And probably in your homework, I'll do one image based, and then we'll go from there. All right. So some of these are more complex than others. For instance, problem 10, a model that translates text and speech from one language to another language. That's a little bit more challenging to think about, and how to arrive at that X and Y. Okay. But let's start with, I like to start with this one. So number 8, a classification model for the detection of Airbus A320 passenger jets while in flight. Okay, for whatever reason, this is I find it easy to think about such things, right? So, and it's a good example to get the dimensions of that X and Y going. All right, so once again, the procedure is simple template. For the following problems, identify and or define the following: the X matrix, the Y vector. What are the samples? That's important. Sometimes it's really easy, but not always. Remind me to do the network security one, actually, because that's a good example of how to define a sample. The classes, and define a set of features. Define the dimensions of X and Y and indicate what they mean. This is really important, okay? All right, so let's go ahead and do that one. So a flight model, a classification model for the detection of Airbus A320 passenger jets while in flight. So I need to switch to the whiteboard here. How do I do it? Here it is, whiteboard, sorry. Okay. All right, so we'll start. So hopefully this works, right? Okay, it's working. So you guys can see this, right? Okay, so again, this is an images problem. I usually just like to start like this, the X and the Y, and just specify the dimensions. You don't even really have to like know everything that you need, just draw this, right? So, okay, let's think about the problem, right? So it's a classification problem. We want to detect A320. So A320s is an airplane. I like airplanes, right? So it's a jet in the air, like a passenger jet. Okay, so it's flying in the air. So basically that means you're on the ground probably, and you have a camera or something. So the camera, don't worry about tracking, it can track. But the point is, it looks at, if it sees an airplane, the camera says, got it. All right. And then from there, it just needs to say that's an A320 versus a private jet or a helicopter, maybe, or a fighter jet, something like that. Right. So that's what you have to think about. You have to detect A320s. So your input is going to be images. Okay. Images. Or, you have to think, are they color images, black and white images? Well, you can simplify things by starting with black and white images. However, if you do that, you may lose some information. Color is very useful. So we have to think about how that works. You guys see that? So you have to make those decisions. You have to think about the dimensions. So anyway, let's start with your classifying, right? So we've identified that. So how many classes do you have for this problem? 2 classes, because the question says, and this is the whole thing, right? You could say I have 10 classes, helicopter, private jet, but the problem is not asking for that, right? The problem is only asking for A320. So I would just make it a binary classification problem. That's going to make your life easier, okay? Maybe make that first and then expand to other things, but you can start with that. So we have 2 classes. So then we can write in here 0, 1, 1, 0, ... Do you see that? So we have that. Okay, then we know that the dimension for this one is 1. Okay, now we have to think about the other dimensions. So we know that an image, let's say that an image, first of all, is black and white, right? So your camera could have, could be 4K or 8K or whatever that is. And that's great. Keep in mind, even though machine learning seems like it's very advanced today, machine learning algorithms cannot train on 4K or 8K. It's too much information. There are constraints in RAM and in GPU, right? So as it stands right now, I haven't checked, but probably today I'm going to estimate that you can train reasonably well a machine learning algorithm with images of 1,000 by 1,000. That's pixels. Okay, 1,000 by 1,000. Okay, does that make sense? 1,000 by 1,000 from 8K. That's very small, actually. But that's, that's where we are. So what you would have to do with your images is if they were 4K, 8K, is you have to compress them a little bit, right? So here is the limitations of where we are today. Maybe 10 years from now, the computers will be so powerful that they'll process 4K, but then we might have 30K, right? Or something, who knows? Anyway, so these are decisions you have to make, but have to think about this, right? Some of those pre-trained models actually are built on images that are 220 by 220 pixels. Okay, so this is really important, defining the dimensions of your images, making sure that these are consistent. What you have to, here you have the advantage because you're using your camera, so all your images are going to be the same size, all right? Even if you had images of different sizes, you'd have to somehow find a way to make them all of the same size. These are important things in machine learning. All right, so when you have these images, the first thing we have to do is define the size of the image. To keep it simple, so I know these multiplications, I'm going to say these are, what? 28 by 28? What is 28 by 28? What is 28 by 28? 784, okay, great. You'll see why I'm doing this math in my head later, but this is actually really important, okay? So in general, you do want the images to be square. That's another thing that, you need to start to make assumptions, right? And that determines how your data is going to be. All right, so you're building this system to detect A320s. Let's say that you are doing this research for a university and you're going to get 4 cameras or something like that, and you're going to put them in various locations here in Hammond. And this project is going to last 2 years. How many images can you collect during that time, do you think? Hmm?
More than a million.
A million in 2 years? Okay, all right. So every day, 4 cameras. Maybe a million. Let's keep it at a little bit less than a million. If you were Facebook or you were Google, I would say, yeah, a million, probably 10 million, a billion, right? Because they have a lot of data. But when you're, if you're doing research here at the university and you say a million and promise that, you may not be able to meet that goal. You'll see how complex it is to deal with data. Okay, does that make sense, guys? So these are the very real issues that you're going to run into, right? So again, let's stick with that scenario. So as I said, if you were Facebook, you can say a million. But if you make an assumption that you're just doing the work here, I would probably question you and say, yeah, probably a little bit less than that. Hmm? Yeah, 3,000. Let's say 10,000 for the sake of argument. So that's 10,000 images. Now you're taking an image and classifying it as A320 or not A320. So if I ask you, what is the sample here? What would you say? What are your samples?
10,000.
You have 10,000 samples, right? So every image is a sample. Very good. All right. So remember that the samples usually translate to the rows. Okay. And if this is 10,000, then this one is also 10,000 because they have to match. Make sense, guys? Make sense? All right. Now, the only thing that's missing is this one, right? So this is N, so this is M. So what is the size of the columns? And you have to remember, so what were the columns in this X matrix? Do you guys remember from last week? The features, very good, the features, right? They are the descriptors that define a sample. Got it? And so we've said that an image is a sample. So then, how many features do you have for an image? And I'm telling you that the images are 28 by 28. They're just, so it's like a picture. Imagine there's an airplane flying. And then the rest is probably blue sky, maybe a cloud there, something like that. You see that? So every image currently is black and white and is 28 by 28. So then how many features do you have? One for each pixel, right? So that's one way of thinking about it. In the past, 10, 15 years ago, people would create a whole bunch of algorithms, 10 different algorithms, and they would go into that image and extract pieces of information from them, right? Nowadays, a lot of people in deep learning, because they have so much computing power and so many images, they just give it the whole image. Maybe compressed, right? Maybe if it was 4K or whatever, it's made into 320 by 320, but otherwise, they just give it that. All right, so if we know that, you guys know what a pixel is in an image, right? So it's the little square, right? And there's 28 by 28 of those, right? And then you have in there what? It's values from 0 to 255, which are called grayscale values. All right, so then how do you encode this? So there are several ways. The simplest way is to kind of stretch this square into a single vector. I usually call this spaghettify, right? So you grab, or imagine you have a piece of like cloth or something with 2 strings and you pull them and then you just end up with the string, right? So that's the same thing. So I'll just do this once here. We're going to convert this into a vector. So I would grab the first row. You see that? And I would do that. That's size 28. You see that? Then I grab the next row of the image and I'll just concatenate it at the end. And that's another 28. Do you see that? And then I do one more like that. And I just do this ... all the way to the end where yeah, exactly. So and I grab the last one. So all of these are basically blocks of size 28, right? And there are 1, 2, 3, 28 of them, right? So that's why 28 by 28 is 784. There was no loss of information. Does that make sense? We as humans need to look at an image like in 2 dimensions to kind of figure things out. But for a machine learning algorithm, this can be sufficient. Got it? Everyone with me on that? All right. So then now that you know this information, what is, oops, sorry. Now that you know this information, what is the size of M? 784. Very good. 784. Do you see that? And, this has many names. I just call it spaghettify. It's fun to call it that. But, you can call it whatever you want. Just bear in mind is this process over here of doing from this to that. Okay? And if we had color images, then that means that we would have 3 grids for the R, the G, and the B. Each of them would be of 28 by 28 in this case. So it'd be 784 times 3, right? Whatever that is. And you can just put the R and then the G and the B and so on. And that's fine. Got it? What's important is that you're consistent in what you're doing, right? And things like that. So now we've identified that our image, so we have X defined as 10,000 by 784. Does that make sense? And that's really important because everything that we're going to do this semester comes down to these numbers. Okay, very critical that you understand this. And then in the second half of today, you'll see what I'm talking about. Okay, we'll start building that muscle memory on how to do tensor operations. So a tensor is just basically a matrix, a vector, or a multi-dimensional matrix, right? That's all it is. And then you're doing operations on them. Okay, so in the past, you probably, remember in your coding examples, you would take 2 for loops and iterate through a 2-dimensional array, but that's inefficient in when you're dealing with massive amounts of data, right? That would be totally inefficient to do it on the CPU like that. So we have to do it in other ways by knowing how to perform these matrix operations. Okay? All right, that's basically it. So did we solve this problem? Am I missing anything? So we had to define the samples, we had to define X and Y, right? And we had to define the classes 0 and 1 and so on. Okay, so that's what these word problems are about. Okay, any questions before we move on to another one? Nope. All right, so let's look at another one here. I need to create a new sheet. Yeah, go ahead, please.
We have different
Yeah, that's a good question. So how do you provide the labels, right? So a human, hire people. It's very expensive to collect data. So but actually there's a cheap way of doing it too. So the expensive way of this is called labeling the data, is you would basically take, let's say you have the camera and the camera is looking at a blue sky, right? So when it sees that something moves in there, it triggers and it takes a picture, right? At least you have that automated. Then you did that and you collected 10,000 of those. Now you have to hire this, the best way, I guess, because it will be exact, is to hire a person to look at these 10,000 pictures and say, oh yeah, because they know that looks like a A320, I think. And that looks like a helicopter, so it would just be the other class. Another way that you could do it in a fully automated way is that all airplanes nowadays have ADS-B, which is a transponder kind of a thing via radio. So they're transmitting what they are. So then if you had that radio, you'd be able to figure out, oh, that's an A320 or not, at least. Make sense? Yeah. But yeah, actually you brought up the point that labeling anything is super expensive. Like imagine if I had 10,000 images and it takes, I don't know, a few hours to label these. That's money that you have to spend, right? For people to look them over and so on. Imagine if it was 1 million like you wanted, that's even more expensive, right? Make sense? Yeah, good question though. All right, any other questions before we move on to another problem? So this was like the super easy kind, right? If you have images, it's always like this. You just have to figure out what are the dimensions of the image, and then you deal with it. Now, there are algorithms that take the images as matrices instead of the way that I was doing the vector. But these are, other techniques like CNNs. We'll talk about them later, and then you'll see how this is loaded. I'm just keeping it very simple right now. Yes, you had a question. Yeah. Yeah.
have a question. Is it like the classes, one is gonna define that it is Airbus, A320 or like, it's not?
Yeah, that's actually what I was keeping it simple. So the problem just said find A320. So then you just say that's an A320, that's a bird, so it's the other class. That's an A320, that's a helicopter, the other class. So one or the other.
We're gonna fix the people.
Those labels? Yeah, you're the architect. It's your project, so. That's right. You're building a model. Remember, machine learning is about correlation. So you're giving it an image and then you're only giving it a 0 or a 1 or a -1 and a 1. You define that because you annotated that. Yeah. If it was the ADS-B thing and they're transmitting what they are, then you can do an if statement and it says helicopter, Airbus, whatever, and then you have maybe 10 classes. And that's a different kind of a problem. But that's up to you. Yeah. Any other questions, guys? All right, so I think that's good enough. So as I said, we're going to do a few problems until we run out of time for the first half, but I think you guys will get the idea. Let's go back now to the bright space. Okay. All right, so let's go back to bright space here. And let's look at it. Here we are. Another problem. Let's do, I think I have a network security one here. Okay, I guess I forgot to include that one, but let's do that one because I've always liked that one because the sample definition is more difficult here. Okay, so let's imagine that I have a problem 11, and you work for a security company, something like that. And the medium that you're analyzing is the network, right? So in the network, instead of images, the information will come usually from packets. You guys know that, right? Like a network traffic is represented by packets, TCP packets, all that stuff. So you have that kind of source of information. Okay, that will be your medium. All right, so then basically you're trying to build a network intrusion detection system. Your data is in packets, network packets, right? So once again, we're going to think about that problem and just create that. Okay, so let's go ahead and go to the whiteboard. Okay. All right, so all right, so let's once again, X and Y. X and Y. The same process, right? We're going to repeat the same process, but we're trying to build a network intrusion detection system. So an intrusion detection does what? It's like, you're sitting there and it detects intrusion, not intrusion, right? That's what? A classification problem. It's like naturally a classification problem, right? In every sense of the word. So how many classes do you have? For this kind of problem, probably intrusion, not intrusion. So once again, a binary classification problem. Do you guys see that? Same idea. All right, now, key questions. Again, we're going to define the N. Oops, yeah, the M, right? And what is a sample? So this problem I always like because defining, if you've never thought about intrusion, maybe the first time that I thought about intrusion detection systems, I spent a little bit of time thinking about what is a sample here, right? So there's a simple answer, and then there's a much more complex answer because it may make more sense to try different kinds of samples than the classic option. So basically, what is an intrusion detection system? So you have a company, right? So this is a company, everyone's working, stuff is happening. There's a lot of network traffic. right? Network cables or something. One of those cables is connected to a computer, right? And that computer looks at all the packets, right? Something like that. And then boom, it looks at information and it says, everything's fine, everything's fine. I looked at this. This looks like an intrusion or something bad in the network. So it generates that information. Okay, so you have to think about it like that. So basically, let's imagine there's some kind of a pipe and there's packets going there, right, in some direction. And then you tap into that line and you look at it and you issue either everything's okay or I found an intrusion. Okay, so we're going to go with that. So then, first question to answer, what is a sample? A packet? One? The number of packets in the pipe. The number of packets. See, there you go. So both you have different answers now, and you're changing the definition of a sample. This is what I was getting at, right? So the simple thing is to say one packet, right? You say one packet, or what if it's like a denial of service attack? Does it help to just look at one packet? Maybe not, right? Maybe you need a context of multiple packets in a time window. Do you see that? So it makes it a little bit more difficult. Okay, got it? So let's go with so if you did one packet, then basically we got one packet. Think about how many packets you can collect in 1 hour, right? That's in a busy network like the university, for instance. That would definitely be millions, right? That would be a lot of information. And that may not be what you want necessarily. So let's just make the problem a little bit more difficult by defining our sample to be, I think somebody said, n packets n packets per what, minute, 10 minutes? Let's say minute, just minute. Okay. So n packets per minute. And we don't really know how many packets per minute, because sometimes you may have 10 packets or you could have 100,000 packets. It just depends, right? But this creates challenges. Because the thing with machine learning is that things need to be consistent because you need to have these dimensions. You can't have variable length dimensions here. For instance, in the example of 10, let's say that you're looking at packets per minute, right? Okay. What if you just have 10 packets in 1 minute, and then in the other one you have 100 packets? Can you do something like this? Just concatenate the packets? Let's say this goes to 10. And then the other one at the other minute, it goes to 100. You'd have variable length samples. Do you see what I'm saying? And that's not going to work. So what's the solution here? Average. Very good. Nice answer. It's the simplest solution that I would just say start there. Average them out. That may lose some information, however, so you may have to try other things. But for this scenario, to keep it simple, average it out. You see what I'm saying? So yeah, so it's like, how you might have, this is a bad example, but you have packets that are going to port 80 all the time. So it'll average out to port 80. Whereas other packets might be going to a high packet port like 40,000. So it'll average out to around 40,000. You see that? So that's just for one feature. Everyone with me? But the point of this is to understand that defining the samples can sometimes be difficult and you have to spend a lot of time thinking about it. But for now, we're going to say that we're going to take every packet and average it. Also, if you know a little bit about the network, you have TCP packets, UDP packets, ICMP packets. So you need to define, okay, is it just TCP packets, for instance? Or do you have 3 models, one for TCP, one for UDP, one for ICMP, which might be a good solution. Okay? Got it? So let's keep it simple. TCP packets, we're going to collect n packets per minute, and that's a time window approach. That's the definition of your sample. Now the question is let's go with something easy. How many samples can you collect, do you think? Not in a minute, but just for the whole, let's say you're going to run this again in like a research environment here at the university, and the project is going to last 3 months. And they give you permission or something to gather the data. So how many packets do you think? Here you might have more than 10,000, right? Because it's the network, there's lots of packets. Let's go with 1,000,000 here. Just, it doesn't matter, right? So just try a different number. So 1,000,000. That means 1,000,000 over here, right? For the labels. This will take us to something, actually you had asked this question, but here's a little bit more difficult. Okay, so we've got this. What about N? What was N again? The feature, right? Features, the descriptors of every single packet here. So what would be the features? Let's keep it simple. They're all TCP. So this is the model only for TCP. So what would be the features, do you think? One? Just how many features will you have and what are they? Just give me a few examples. Port numbers, right? Destination port, source port. You may need to process that a little bit more robustly, but just to keep it as source port, destination port, number of bytes sent, number of bytes received. You see that's 4 features. So it's just things. Where do you have to go in to get this data? Look at the packet. You'll have to understand how TCP packets are, how they work, all the headers that they have. Do you see what I'm saying? And you extract that data from there. The key thing is every packet that you look at always should have a source port and a destination port, because remember, you're going to be averaging. So you can't have, 19 packets that have source port and one that doesn't have it. Then you'll have like garbage. Garbage in, garbage out, right? So you have to make sure that this is very precise. Payload, you could look at payload, but then you have to think about how that's going to work. Okay, so let's exclude payload for this example, just to keep it simple. Okay, so source port, destination port, byte sent, bytes received, and a few more things. Let's say there's 10 features that we're going to extract, and we're going to average those out. So for all the packets that we collect in 1 minute. So based on that, what is M equal to? 10, exactly, 10. Very good. Do you see that? I mean, is that the best solution? I'm not saying it is, but it's all that I care about right now is understanding these dimensions. Maybe that's your first pass. The next time around, you're going to have better ideas on how to do this. That's what they hire you to do, right? To figure this out. And you have to go in and read blogs, read papers, watch YouTube videos, whatever it is, see what others have done, and then make a decision on how you're going to do this. Got it? All right. So we know that we have 1,000,000 by 10, right, is X. And then Y would be 1,000,000 by 1. We've defined a sample. So the last thing probably is how do we annotate the data? These labels. Because remember, you're going to train a model to predict these, right? To give you a 0 or a 1 and so on. But how do you label it? Can you hire a couple of students to do this? It's 1,000,000 packets. Do you think they would even want to do it? Probably not, right? That's a very tedious job. So in this kind of problem, you probably need to automate it somehow. So this takes us very likely to the problem of imbalanced data sets, okay? So what does that mean? So usually a lot of the data sets that we're going to cover in this course are going to be balanced. And what that means is, like, if I have a 2-class problem, you're going to have half of one class, half of the other class. In reality, though, you rarely have balanced data sets. And that actually will create many, many problems for you, because machine learning is really made to distinguish between one thing and the other. So you really want the same amount of samples on one class or the other class, or multiple classes. But in this case, it's very easy, or at least somewhat easy, to get examples of one class, right? The class are related to good traffic. Why? Because all of you guys are on the network probably right now, or you were during the last hour, and I don't think any of you were attacking the university, right? Hopefully, right? So if you weren't doing that, that means all of your traffic, you can safely assume, is good network traffic. So we would be able to collect a lot of samples of that. The challenge is, how do we then collect bad samples. First of all, the university will not allow you to take some tool and start attacking it. That's, violation of the policy, first of all, right? So then how do you collect that data? So and if they were attacked and for real, it's only going to be a few attacks, 10 attacks to the 1 million. That's a highly imbalanced data set. You see, so before you ever take a problem like that, think about that, right? Because it's very challenging. So what may have to happen is you're going to have to simulate a network, attack that, and collect some packets like that. Do you see that? If you were collecting your data. Does that make sense? Any questions about that? All right. So again, we're not going to go deeper than that, but that's, something to consider when you're looking at these machine learning problems. All right. Before I move on to another problem, are there any questions? It's starting to make sense, right? What you have to do for the homework. Okay. All right. Let's do one. And I think we have time maybe for a couple more. All right. So I'm not hearing any questions. And then we'll finish this section and move on, start tensor operations during the second half. Yes, sir, please.
Just wondering, even for this exam, simplistic example that you're using,
it's the simplest solution.
Interestingly, you mentioned we should not include payload, but we should include source and port numbers. I don't think averaging source port numbers makes sense. Averaging payload may make sense. I think shouldn't it be like the opposite?
No, I agree with you. So I'm trying to simplify it. So, because really averaging source port destination falls back to that idea of, port 22 is not more than port 10 or port 6 or port 80 is not more than port 22. There is no relationship there. So this is a categorical data, right? So you'd really then, if you have source port, okay, break it into like 1,000 ports, and now you have 1,000 features. Do you see what I'm saying? So you could do that. Source and bytes received, you would average. But I asked you this question, so I'm going to throw this back at you, okay? So I said just average it because that makes it nicely 1 million by 10. What else can I do? If I don't average it, because I still need to define what a sample is, right? And I'm saying I'm collecting n packets per minute, but they are variable. Sometimes you can have more, sometimes you can have less. So without averaging, what's an alternative solution that you can think of? Okay. So so you're suggesting having a set of algorithms that looks at the packet and extracts something from it, right? Okay. But so again, the easiest question I can ask you is, what is M then in your scenario? Because that allows me to understand your approach, right?
In this case, the M could be the same as we discussed, but for
Okay. So you're still, got it. Okay. So you average something. So his solution is vectors of still 10, where some are averaged, but some, like, you collected 17 packets. So you calculate like the median, max, min, so a few more statistical descriptors.
Yeah, I mean, for categorical features like source, probably better to get a mode or median. For numerical features, probably better to add
Average. Yeah. Okay. So you can add more complexity to it, and that's perfectly fine. Yeah. Any other questions, guys? Okay. All right. Great questions. All right. So let's move on then. We're going to do another problem. So let's, I need to stop here. Okay. All right, so let's read some of the. All right, so let's see what classification. Let's not do images anymore because we've done that. Image. Which one? Weather monitoring. Which one is that? 6? So that would be sensors, and I'm looking for things that are different in the representation. So this would be sensors, right? And then we would say what? What's the temperature? Sure, let's do weather monitoring. And then hopefully we'll have time for one more. That's fine. All right, so I'm gonna do, so let's see, 6, a classification model for weather monitoring. Stop. I'm gonna do, no, sorry. Okay. All right, so weather monitoring, right? So again, we have to start thinking about the problem, X and Y. So why do we need a weather monitoring system? Let's say that you're airports, right? Airports, people that fly, they need to have a weather monitoring system to know if they should fly that day or not. Let's think of like general aviation, right? So private pilots and things like that. So some little airport somewhere, they'll need to have a weather station there and then, provide some information. So let's keep it interesting. What would a pilot need? Probably they need to know wind speed. They need to know how cold it is, the dew point, you know what I mean? Like the density, how cloudy it is, those kinds of things, right? So let's say, okay, we're trying to predict 4 to 5 things. Let's say 4 things. And I've already mentioned, these are the things we're trying to predict. So I said temperature, what did I say? Wind velocity. Huh? Direction of the wind, sure. Wind direction, that's a good one. Humidity. Yeah, let's just keep it at 4. Just keep it simple. So we're trying to predict 4 things. Okay, the model needs to tell you these, right? Okay, so again, we need to define X and Y. So N and M, right? So how is this going to work? The weather station at that local airport will have somewhat sensors, right? Let's not get into like the physics and science of this. It's not overcomplicated, right? Let's make up these machines. They exist, okay? And they can tell you some characteristics to predict temperature and this. So what would it be? What would they look at? Do this.
Readings per minute or
Huh?
readings per particular time.
Yeah, but remember, we're building a machine learning algorithm, right? So it's predicting these things. I know, but I've made it so it predicts these. It's kind of a made up. How about we do this? A camera takes a picture, right? It doesn't matter if it's good or bad, right? So the camera takes a picture of the airport from and then it predicts these values because it can measure them, right? Remember, it's machine learning. So it needs to, given an input, predict an output, right? You guys see what I'm saying? So we're going to assume that it's a camera that takes a picture of the airport. So again, then, you need to define the dimensions of this, right? So let's say it is, again, just because I know the number, 28 by 28, right? So then this is going to be 784. So this is 784. And how many of these can we take? N. We have a what, sir? Oh, the object detection for this? Yeah, but let's just keep it simple, right? So let's just think about this. So how many samples would we have? Let's say we can have 1 million because we can have a lot, right? And then we would take an image of size 784. The key thing is we're trying to predict 4 things, okay? 4 values. These values, temperature, wind velocity, wind distance, and wind direction, yeah, and humidity. What are they? Like, what are some examples of temperature? It's going to be like 32, 40, something like that. What about wind velocity? It's going to be what? 7, 15, 23, right? What about wind direction? north, south, east, west, right? Categorical data, right? Like northeast, northwest. Let's keep it simple. North, south, east, west. Just, but yeah, good. North. So you probably see where I'm going with this. So I'm just, as I said, I'm trying to like make these different, right? And what about humidity? That's usually a number, right?
Yeah.
I don't know. What's an example of humidity? Huh? 50%. Okay. Or it could be 60%, 70. Okay, great. So what I'm trying to show you here is this model you could create if you wanted to. That's perfectly fine. Will it work? I don't know. It doesn't matter, right? In this example, if it works, go start a company. All right. So these three are regression values. Do you guys see that? So they're regression. That means that you're going to create a model that always predicts real valued numbers, right? A 60, 65. This one could be a classification problem if you want, because you're doing north, south, east, west. Do you see that, guys? Now, could you, in theory, create a model, one single model that predicts these four values? Yes, you could. I mean, I don't know that it'll work, but you could. In that case, you would have, you know, this, I'm trying to show you that your X, you know, is always 1,000, n by m, but your Y doesn't always have to be n by 1, right? It could be n by 4 in this case. N by 4, where this one would be temperature, this one would be wind velocity, this one would be wind distance, and this one would be humidity. And you could do that. I would probably do the three regression ones in one model and then the classification one in another model, or even better, I would do 4 separate models. But you could, in theory, in one single model, for whatever reason, predict the 3 regression values together. That's called a multi-output regression problem. We may do that during this semester. No, I think you had a question.
Get rid of one direction. I said,
Wow, yeah, there you go. That's true. Yeah. That's exactly. Yeah, I mean, when I've done multiple output regression, I like that because I just have to train one model. So it's a thing I like. But probably what's happening, unfortunately, is that it's getting one output good, but it's taking away of the other ones. Think of it as a seesaw, right? Because the weights are the same for both problems. So it might have a little bit of trouble. So you can sometimes squeeze a little bit of performance by just creating separate models. But it's perfectly possible to do one output as well. Does this make sense, guys? Did you want to see something else related to this problem? Again, it's just, you know, thinking of different ways of doing this. Yes, sir, please.
I think we could also use trend information, like.
We could use what?
Trend information, like, or basically, what was the temperature in the past hour? Temperature in the 30 minutes, then basically focus.
But that's what kind of you're introducing a new kind of problem. What is that called? It's called a time series problem. And that's different from this.
I mean, we don't necessarily need to have it in a time, like, we don't need to provide all the inputs for the past hour. Just aggregate all the temperature values during, let's say, the past hour. Or
The past hour.
Basically, it just gives sort of like a trend information. Then say with the velocity.
Let's do that. It's a good example. Let's do that, right? So what he's proposing, so I would think immediately time series problem, but time series problem requires another set of algorithms that are sequential, that look at previous things and use that to predict. And there's a problem there because if you're predicting like 3 weeks in advance, you need to predict those weeks and use that information to predict the next one. And you may be introducing some error. He's proposing something a little bit different. So let's do that one. And you can help me out here. Just give me a second to get a new sheet. Let me just close this thing and open it. Right, so. All right, so we're going to predict weather using weather. So we're gonna predict rain okay? So, and we're gonna use X and Y still, okay? Okay. So let's keep it to 1, just to keep it simple, temperature. All right, so I'm gonna predict temperature, which is gonna be a regression value, so 32, 40. All right, so what's your suggestion?
Just so we have a bit of trend information, let's have the average temperature within the past 30 minutes and also the average temperature from 30 to 60 minutes. Just so the model has a sense of trend, just these three.
Okay, so, okay, yeah, so from the previous hour, from 0 to 30 and 30 to 60, right? Okay, and then we're gonna take yeah, we take the average, we have a sensor that measures temperature every 5 minutes. So that would be 6, right? 6, and then we average it. Do you guys see that? Guys, does that make sense for everyone? Okay, so how do you propose? That's a good one. You know, I like that problem because that could be a problem in the exam, right? And I ask you to define X and Y. So you need to tell me, guys, everyone with me? You need to tell me what N is and what M is. And again, that's what I love about this method is that, you know, it provides clarity, right? So what is M in your example? The number?
M would be just 2
2,
meters.
okay? You see how simple it is. Something that may have been abstract to understand, now it's clear. There's just 2 values in there, okay? And so 2 columns, and then you just define that you collect every 5 minutes from 0 to 30, the samples and average them. So that's going to be maybe, let's say 30. And then in the next one, you take another 6, average them, and that was 31. And you can see then basically this model, you give it that as an input and it tells you 32. Do you guys see that? Does that make sense for everyone? Okay. Okay, so I have one question for you, but let's just to finish this one. What is N here? What is N? 10,000. Yeah, 10,000. So just reasonably, it's some weather station. It's collecting every 5 minutes. You have to do the math, and then you can determine. So, final question: what's a sample here?
It's basically just the aggregated average temperatures of 2 time windows.
Yeah.
One is the past 30 minutes, one is from past 30 to 60
Yeah.
minutes.
So you see, that's a much more complex sample that you had to define. Does that make sense, guys? Any questions? All right, good example. We have 3 more minutes, okay? So in the last 3 minutes, I'll just talk about one of these problems. Because I think you guys get the hang of the procedure. So let me just pick one more. So we need to go to the document. All right, so third one. I think that's an easy one. I'm looking for more difficult ones. Like for instance, number 5 and number 10 are difficult problems. Yeah, the Netflix one is difficult. And then, but let's do 10 actually. Let's do 10. A model that translates, and let's just keep it at text, not speech, translates text from one language to another language. That's a tough one, right? So how do you even begin to do this with the mechanism that you know about? Translates text from one language to another language. So let's say you're translating from English to Chinese or something like that. Following this procedure of X and Y, right? Where, you know, how does this work? Remember, you're trying to correlate one thing to another. You're translating from one language to another, probably to keep it simple, let's use sentences. You have one sentence and you have another sentence. So this is a sentence in English and this is a sentence in Chinese, right? So the simplest thing you can think of is what? Let's define samples as a sentence. Make sense? So I would need to encode somehow an English sentence, right? And then, so let's say English goes here. Where does Chinese go? And how does it get represented here? What do you guys think? And you need to tell me in terms of M by N, right? That's the key. Any ideas? How do you do it? Alphabets? Okay.
Number of characters.
Number of characters, sure, but give me M by N. The words? How many words? Okay, I like that idea. 5,000 words of English, 5,000 words of Chinese. How about that? It's not gonna be a great translator, right? But it's gonna work. So what I mean by that is, do you guys know how to create a new page on this thing? I think it's maybe this. Yeah, there we go. All right, that page. Give me a sec. Okay, yeah, go ahead. Yeah, it's not directly one-to-one. You are right. Yeah, I like that. But let's go with this. I like the idea of 5,000 and 5,000. I think it's a simple solution. So what does that mean? We're saying that every sentence is a sample, and we need to have the descriptors for the sentence. What that mean, the features, right? And the features are gonna be a vocabulary of 5,000 each. So then, one way of thinking about this could be, may not be the best solution, but this one is 5,000, this one is 5,000. Do you see that? It's gonna be, so word 1 to word 5,000 and word 1 to word 5,000. Just keep in mind, this is word 1 in English and word 1 in Chinese to word 5,000 in Chinese. Do you guys see that? So a sample is those pairs. You train that, like that correlation, right? And then hopefully the next time you give it a vector of the 5,000 English words, it's gonna try to produce a vector of the 5,000 Chinese words, and boom, you have a translator. Do you see that, guys? Does that make sense? Now, how would this be represented? This would be represented probably by zeros and ones. So what that means is, think about it. This is a very sparse vector because you're going to have 5,000 features, but usually how many words do you have in a sentence on average? 10. So that vector will have 10 ones somewhere in there, and the rest, 4,000 something zeros. Does that make sense? And the same goes for the Chinese vector. Will have 5,000, maybe, as you said, right? You know, a sentence in English might translate, a sentence in English of 10 words might translate to a sentence in Chinese of 12 words. I don't know. But that's fine. That's, you know, we're building this in such a way that it could do it, in theory. Got it? Now, how many samples do you think? So we need to, so that we answer M, then we need to answer N. How many samples do you think we need to have here for this to actually work? But work it with some millions. That's a very good answer, right? So here, if you just give it 100, it's not gonna. This one, let's say it needs 10 million. Probably needs more.
It's the combination of 5,000.
Yeah, it's learning to remember, it's correlating, right? It needs to learn to correlate this vector to those vectors. It basically needs to learn to correlate vectors of 5,000 to vectors of 5,000. If we look at this from the point of view of the neural network, this is actually like a nice, what would this neural network look like? It would be 5,000 English, something in the neural network going on, and your output vector, the Chinese, would also be 5,000. You see that? 5,000 to 5,000. That's why this is really important, because now when you start to define your architecture, it will need to look like this. Got it, guys? Does that make sense? All right, so hopefully these problems made sense. We'll stop this half of the lecture here. So it's 6:25. So we'll take a 10-minute break until 6:35. Okay, this concludes the word problems. So now I'll just give you a homework assignment of 3 to 5. I'll create it tomorrow probably, and it'll be due a week from today. Okay, got it? So I'll add the link later. All right, okay. Any questions? All right, let's take a 10-minute break. We'll start at 7:25 and just look at the second half of today. 6:30, what did I say? Oh, did I? Thinking of going home. All right, so I'm gonna stop here the video.